We're here for another video and we will be talking about free body diagrams. Now, what are free body diagrams? So a free body diagram, basically it's a visual representation. It's a physical model of an object that is affected by several forces, including all of the contact forces and non-contact forces. A free body diagram can also be called as a force diagram. Your free body diagrams are important in analyzing objects on how forces influence their state of motion because it gives us a clear picture on the different forces present that are acting on that object and how are these forces oriented with respect to that object and how does it affect the state of motion of that object. So what are some of the guides that we should remember in drawing free body diagrams? Number one, you need to draw the object under consideration. The object or the drawing needs not to be artistic. So you can use box, you can use a circle, you can use a point to represent that object. It's just a physical representation. So, for example, if we are analyzing the forces acting on, let's say, a train, you need not to draw the train. We just need to draw something that can represent that train, either a rectangle, a point, or whatever shape that is usable or that can easily be drawn, but not too confusing. Next, we need to include all of the forces that acts on the object. So you need to, although we need to isolate that one object in consideration, we need also to look into its environment on what are the forces that might be exerted by the objects around it to that object in consideration. So we need to include all of that. And when we represent force, remember force is a vector. So when we represent force, we represent it with an arrow. And remember that when you represent vectors in arrows, your length of the arrow represents the magnitude of the force, while the arrowhead represents the direction of the force. Next, convert the free body diagram into a more detailed diagram showing the x and y components of a given force, because there will be forces that might be exerted at an angle. So therefore, we need to resolve them into components so that we can solve for the net force of or the net force that is acting on that object in consideration. And then if there are two or more objects in the system, then we need to draw a separate free body diagram for each of that object. So let's take a look at some examples. So you have here a sled, which is 15 kilograms. So a sled here is exerted with the force P at 30 degrees. So in this case, we represented our sled at this point, or using this point here. So we know that there's an applied force here directed at 30 degrees from the horizontal. So let's say this is the horizontal there. So it's at 30 degrees. That is your applied force. Now, it's not just the applied force that is present on that sled, because the sled sits on the ground, or it's on the ground. And also, your sled has mass. And if something has mass, then it will have weight, since it will be acted upon by the attraction force of objects around it. And in this case, the gravitational force that is not negligible will be the gravitational force exerted by the Earth. So therefore, your sled has weight, which is your gravitational force. And since it's on a surface, then your sled will also be exerted by a normal force, which is perpendicular and away to that surface. Now, keep in mind that since your sled is not moving up or down, or it's not accelerated up or down, then your weight and normal force should balance out each other. Aside from that, you have a friction force. Since we did not state that, or we did not assume that our surface is frictionless, then there must be a friction force. And remember, friction force will be opposite from your applied force, or opposite to the direction of the force that is being applied, either be it a tension force or an applied force or a spring force, etc. So this will be our free body diagram. But you have here your applied force, which can be resolved into its x and y components so that we can solve for its net, or we can solve for the net force that is acting on the sled. So you have here your applied force along the x and your applied force along the y-axis. So this will be your free body diagram. And again, you can illustrate this free body diagram. You can represent the sled using a box or a circle or any shape that will be easier for us to represent that sled, or a point if we treat it as a particle. Another example, a rope pulls a bucket upward at a constant speed, and we ignore air resistance. Looking into your lesson in Newton's laws of motion, an object that is at rest and an object that is in constant velocity has zero acceleration. And therefore, they have balanced forces. So here it's stated that it's constant speed. So your bucket, as represented by this point, is pulled upward by a rope. Therefore, it has tension force. It is exerted with a tension force. That is the force going up. And you have, of course, the weight of the bucket. That is the force going down. And your tension and weight should balance out each other since it's constant speed. Now, it will be a different situation if it says there that it's accelerating upward. Because if it's accelerating upward, then if we represent your bucket, if this is your bucket, if it's accelerating upward, then you have your tension force, which will be greater than your weight. The net force here will be going up. So therefore, there will be an acceleration going. Next, a block sliding in an inclined plane at constant velocity. So you have here an object that rests on an inclined plane. Now, when an object rests on an inclined plane, of course, this object will have weight still. But your weight will not be projected at an angle. Your weight always is directed downward. So your weight acts downward with respect to that object. Now, your normal force in this case is perpendicular to the surface. So if this is your surface, if that is our surface, then the normal force will be perpendicular to that. So that's your normal force, and this will be weight. Now, since it's sliding, it's important that you consider what's happening in the object and the surroundings of that object. So since it's sliding down, then therefore, there will be friction force opposite to that. So these are the forces acting on the object. Now, we can actually, if we have a Cartesian, or if we assign the x and y axis in this way, x and y axis, you have two forces that will need to be resolved into its components. But remember that directions in our free body diagrams can be arbitrary, or when we assign directions here, we can actually tilt our Cartesian coordinate plane. As you can see here, we assign this one as our x-axis and this will be our y-axis. Now, The one that needs to be resolved into components here is just your weight. The component of the weight that is parallel to the friction force, and the component of the weight that is parallel to the normal force. Now, the angle of inclination in an inclined plane will be the angle between the weight and the weight parallel to the normal force. Solving the components of the weight, so you have here the component, this will be our Cartesian coordinate plane. So you have your x and y. So along the x, the forces along x will be the friction force and the x component of your weight. And for the y-axis, then you have your normal force and the y component of your weight. Next, another example. So you have here two objects, and remember, when you have two objects, we need to represent, or we need to make individual free body diagrams for them. So we have this mass A, and we have, or mass 1 and mass 2. So what will be the free body diagram in these two objects? If we look at it, we can see that the objects are accelerating. So this object is accelerating towards this direction, or to the right, and this one is accelerating downward. So let's make the free body diagram for mass 1. If this is our mass 1, for our mass 1, what will be the forces present on the object? Of course, you have here a string. As you can see here, there's a string that pulls mass 1 to the right. Then therefore, there is tension force going to the right. Now, remember that the mass is accelerating to the right. Therefore, there must be, or if there's a force opposite to that tension, then it must be lesser compared to tension force. Now, since the mass 1, or mass 1 is moving through a surface, then it must have a friction. So the friction force will be acting on the opposite of your tension force. And the friction force is smaller in magnitude compared to the tension force, because again, your object is accelerating towards the right. So there must be a net force. But we're not yet done here. We have your object that is resting on a surface, and your object has a weight. Therefore, your object will need to have this force vector and of course your normal force, which is balanced to that weight. So this will be our free body diagram for mass 1. Now let's move to mass 2. So what will be the free body diagram for the second mass? So if this is our second mass, what are the forces acting on that object? You have the rope here that's pulling the mass upward. Of course, ropes only pull. It will not make any sense if ropes push. So although you see here that your mass 2 is moving downward or accelerating downward, your tension still is a pull force. So therefore, you will have a pull force here. That's your tension. However, it's accelerating downward. Therefore, what will be the force that causes it to accelerate downward? It will be the weight of the object, which should be longer compared to the tension force because it's accelerating downward. Do we have any other forces to factor in here? So it doesn't have any forces. It doesn't have any forces along the x-axis. So this will be our free body diagram. Now, even though it's not part of the free body diagram, you can indicate the acceleration of our objects. So this is our free body diagram for these two. Let's have another example. A ball of mass hangs at rest, suspended by a string. So draw the free body diagram for the ball. So if we have here the ball and it's suspended by a string, then it must have tension force upward. And also your ball has weight. And remember, your tension and weight should be equal. Why? Because your ball hangs at rest. So therefore, the acceleration is zero, or your body is in equilibrium. So that's why your tension and weight should be equal. Next, a car is accelerating to the right along a horizontal road. So a car is accelerating to the right along a horizontal road. So what will be our free body diagram? So if we have here, if we represent the car using this rectangle, so we have the thrust of the car that will cause it to move to the right. The thrust created by the engine of the car, which causes it to move to the right. Now, between the tires and the road, there will be friction. But the friction force will be, your friction force will be lesser compared to the thrust or your force that causes the car to accelerate to the right. Why? Because again, it's accelerating. So there must be a net force going to the right. Now, aside from that, do not forget that our car has mass, which consequently it will have weight. And since it's on a surface, the surface of the road, then it will have a normal force. Although it's not part of the free body diagram, so we can indicate the acceleration of the car. It means that it's accelerating, moving towards the right. So this is our free body diagram. If, well, commonly, we have problems which do not factor in air resistance. If it's stated here to ignore air resistance, so we do not factor in air resistance or the drag force. But if it's stated there that air resistance is important, let's say, for example, we have here, air resistance is important. What do we need to do there? We also need another force that is opposing. Remember, air resistance is a type of friction. So you will have another force here. Oops. We'll have the free body diagram will have another force here, which will be your friction of air. And since it's still accelerating to the right, so the sum of your air friction or air resistance and friction force between the surface should be still less than your thrust. There. So that's how you create a free body diagram. So those are your examples and the things that you need to remember when constructing free body diagram. So I hope that you understood and you already know how to create free body diagrams, and good luck in studying dynamics and of course statics. Thank you very much and bye.